Hello everyone, so today we have a Calculus 3 multivariable calculus problem where we're being asked to find this surface integral, two integrals, vector field f dotted with ds, vector element of the surface area ds, over the surface S, composed of the upper hemisphere, x squared plus y squared plus z squared equals 4, where z is greater than 0, and the circle x squared plus y squared is less than or equal to 4 for z equal to 0. For the vector field f, which has first component xy, comma second component yz, and comma third component xz. All right, so how do I, in terms of computing this, there's a couple ways of doing this. I could do this directly by computing the surface integral over both these surfaces, S1 and S2. So S1 is that hemisphere, and S2 is the circle. And yeah, I have the two little red arrows there because we're denoting flux and we're trying to find the outward flux here, okay? Now, we could do that, or we could use this theorem, which is Gauss's theorem, or the divergence theorem, which says something along these lines. Let S be a closed surface and boundary S, yeah, sorry, I don't know how to say that letter in Greek, that one that looks like, take the partial derivative of this one. So and then you have the boundary of S. And what this theorem says is as follows. If you take the surface integral over the boundary, let's just say change in of S here, for lack of a better word, over the vector field dotted with ds, it's equal to the triple integral over that surface of the divergence of your vector field dv, okay? So essentially it comes down to taking that surface integral, it comes down to integrating over like the volume of the surface of the divergence, integrating over the divergence. Okay, so we're gonna need this in a second for my picture. First, let's figure out the divergence. So the divergence is the partial derivatives of each of the components with respect to x, y, and z, as you see right here. And that came out to be y plus z plus x, okay? And what we're gonna do is we're gonna integrate that over the surface. So the surface, if you notice, yeah, it's a hemisphere really that you're looking at, and the bottom of it is equals 0. So what I would choose to use cylindrical coordinates myself, or spherical. I'm going to use cylindrical here, but spherical would work out as well. Okay, and I would have these limits of integration. And how do I get those? Again, by looking at the picture. Yeah, x squared plus y squared is like saying r squared. So this is like saying r squared plus z squared is 4. And if you were to solve for z, z would equal the square root of 4 minus r squared. So your z's would be between square root of 4 minus r squared and 0. Your r's are between 0 and 2. And your theta would be between 0 and 2 pi. So just refer back to what you know about cylindrical coordinates for this. And we're going to go ahead now. Let's go back over here. And that integral will now become this after integrating with respect to z. So it's going to be r dz dr d theta, and a couple more things. X and y were converted using r sine theta and r cosine theta. Okay, as you can see here for y and then for x. Then I integrated with respect to z first and plugged my limits in, and we're like at this point now when we do that. And one more thing, I went ahead and put the two terms here and here together to give you what you see here. And then special attention to that integral 0 to 2 r squared square root of 4 minus r squared. That is a trig substitution, and these integrals don't get that difficult, but this would be one of the harder ones. You have to use like some trig sub, or you can use Desmos, and your answer would be pi out of this whole thing. Okay. I went ahead and integrated these. I'm not showing the work. And yeah, so we just basically continue integrating this until you reach an answer of 4 pi. So that answer 4 pi, you would have gone the same way if you did the surface integral separately of the hemisphere and the circle. Okay, so nice little shortcut for us. Very important though, you have to have a closed surface. If you don't have a closed surface, this will not work for you. Okay, all right, well, I hope this helps. Thank you for your time.